Welcome back. All right, so I did part one with regards to this test on fluid statics, which is really kind of on density and pressure. So I'm going to put up a link up above there to part number one, which covers the first 4 questions of this test. Now, I'm going to also post, so in the description below, you're going to be able to see and download for yourself this test again. It's also given in part one. Okay, so I'll do that link for you. So now let's just kind of jump in, okay, and do the second half of the test, which is going to be questions 5 all the way through 8. So for question number 5, okay, which is this one. So this is going to be an interesting one because it utilizes Pascal's principle. So basically the pressure, okay, that is applied within a closed or enclosed fluid is transferred undiminished, which is a pretty amazing result, so that you can do quite marvelous things. Okay, for example, applying a very small force to actually start lifting up or jacking up a car, for instance. So here is the example. So we have a vehicle, okay, and this vehicle has a mass of, it's quite a bit, okay, it's about 1.5 tons, which is about 1590 kilograms. Okay, so I'm going to just write that in here. So that's the mass of the vehicle. 1590, this is kilograms, so it's good, it's SI units for us. And now the vehicle is resting on a circular platform with a radius of 50 centimeters. So, I mean, this platform, the way that it's has been kind of drawn, okay, or at least that I have kind of put this together, so this platform looks like it's a lot bigger than that. So there is kind of this particular platform that you might have, okay, in here, and what we're looking for is that it has a radius. And this particular radius is 50 centimeters. Now, of course, you can change that back to meters if you want to. Okay, so that would be just 0.5. Now, the platform is pushed upward by the use of a fluid inside a hydraulics system. So this is, I've kind of drew it out in here for us. Okay, so inside of this, okay, there is a fluid which is going to be, okay, so we're utilizing a force right here. Okay, and it's being transferred, so the pressure is being transferred, okay, and it is pushing this thing upwards. Now, this particular force, okay, that we have, so this F1 that is drawn out in here, it's not very much. So you can see there that the force is 10 pounds, okay, so this is the force that we're pressing out with. So that kind of actually sucks because, okay, so this is not in metric standard, so I mean we can certainly change this back. Okay, so recall 1 Newton is equal to, I'm just going to use this, okay, conversion between the two if you want. I think it's 0.2248 or 45 or something, but rounded to 3. So this is what it would be. So I'm just going to change it right away. Okay, so we have 10 pounds. So if you're going to be changing that back up into newtons, that's going to be divided by really 0.225. Okay, and then I'll just keep this. So this is going to be 44.4. Okay, this is newtons. Now we want to be able to know what the radius, okay, is of this little tiny device in here. Okay, that is being, okay, this force is being applied onto, and we'll see that it's actually very small. And yet, we have 10 pounds, and it's lifting this enormous. Okay, so the weight of this thing is huge. Okay, that we would have. Now, from Pascal's principle, so what we know is, okay, so whenever you have, okay, so because the pressure is undiminished, so basically the change in pressure all the way through is going to be kind of the same. So that 10 pounds, okay, over whatever the surface area is on the left-hand side, okay, is going to give us a certain amount of pressure. Okay, so here, we would have pressure. I'm going to put pressure P1 is going to be the force F1, okay, divided by the area. And that area, okay, is going to be of this. Now, it's asking us for the radius back in centimeters, all right, of what this, circular little path would be, okay, that we are utilizing it. Now, that pressure is being passed on all the way here, okay, and so that the change, okay, so that we would have in there is going to be identical. So whatever pressure you have here is going to be the same pressure, okay, that is applied over here. So this is, I'm going to call this F2, okay, over the area 2. So really what we are dealing with is we have pressure 1 is equal to pressure 2. So that comes from Pascal's principle that we have. We know what the force is. So this is going to be force F1 all over, okay, our area 1. And this is going to be force F2 over the area A2. Now we know quite a lot of information in here. So F2, so we have the weight, so we can transfer this. This is going to be the weight of the vehicle that we have, and that's going to be 1590 multiplied by 9.8. So don't forget, weight is equal to just mass times gravity. So that's the force, okay, that we kind of have to uplift within here. And then the area itself, because we know that it's kind of a circular, so this is going to be pi r squared. And you know, if they want it in centimeters, so I mean we can keep everything in centimeters if we like. Okay, so maybe I'll just keep it in centimeters for this, okay, and then put that in there. So it's not exactly given in metric standard units, but we are trying to solve for the radius, right? And then the radius they want in centimeters. So on the other side, what we have is this is 44 newtons, okay, on the left. So the forces are both in newtons. And then this is going to be pi, and now this is what we're after. Okay, so we want to know what the radius, okay, of this is right there. That's what we want to be able to find out. So notice we only have really just one unknown here. We know everything else in here. So if I go ahead, so actually the pi and the pi will cancel. So that's going to be gone. The r, okay, that we have, so I'm going to multiply both sides, okay, by r1, okay, squared. So this is r1 squared. Okay, so I can do that to both sides, and that's going to get rid of this from here, and we're going to get 44. This, okay, and this, so I can divide both sides by that. So that's going to be 1590 times 9.8. Okay, so that's what we have there. And what that will leave me with is going to be r1 squared, and then this right here, so the radius right here, we no longer need it, so I'm going to bring it over also on the other side. So I'm going to make room for that there. I'm going to multiply, so by this, okay, so this is going to multiply, so it was at the bottom. Now if you multiply both sides by it, it will cancel from one of the sides and it will end up over here. Now with that, this is just numbers, so we have an answer, and now notice the newtons will all cancel each other off, and you're just going to be left with centimeters, which is actually what we want our answer to be. So this is our answer multiplied by, that's going to be 50, and this is squared, and this whole thing is going to be divided by 1590 times 9.8. Okay, so there you have it. Okay, so that's going to be 7. Now this is not our radius yet, because 7, 1, 3, 0, 7, etc. Because this is r1 squared. So we have to take this, and we have to take the square root of this. All right, so the square root is the same thing as taking it to the exponent of a half, or 0.5. And that's going to be a very tiny radius. Okay, so this is 2.67 to 36 figs centimeters. So very, very small, right? The other one was 50, okay, that we would have in here. And that's how you would actually approach and solve this style of question. This is a common question which is asked on tests, quizzes, assignments, etc., because it kind of pushes you in the direction of understanding Pascal's principle, okay, and then the transfer of pressure, okay, through a fluid. So there you have it, okay, so that's question 5 here. Here's the next question. So we have a manometer. So a manometer is basically a device like this, okay, where you're testing out the pressures, okay, on one end, okay, and then you have some kind of a fluid, okay, inside within here, and then the pressure changes, okay, so because of this, it makes the fluid, you know, either go up, okay, so if this pressure is greater than the atmospheric, so it's going to push this fluid, okay, it's going to go up here. Okay, if you sometimes call negative pressure, so this gets pulled back out in here. You can put up a link up above there to some examples and discussion of a manometer. So now let's take a look and see what we have in here. So it says the manometer below provides a reading of 78 millimeters of mercury. Okay, so that's the pressure. Okay, so this is coming from a blood pressure reading, right? So I guess, okay, so this would have been the gauge pressure. So let's just put that in here. Now, so we have 78, millimeters of mercury. So that's the reading we have. Compute the gauge pressure in SI units, assuming that the density of mercury is 13.6 grams per centimeters cubed. So that's going to be the same thing as 13.6 times 10 to the 3. That's going to be kilograms per meter cubed, okay? So that's just density conversions that we have. Now, once you have your answer in pascals, convert it to millimeters of mercury by assuming 1 millimeter of mercury is equal to 133.322 pascals. So that's just the unit conversions. Does your answer match the manometer reading of 78 millimeters? Okay. Well, so first of all, if we know that the manometer reads this, so we already know what the gauge pressure is. So you can, if you're really clever, you don't have to go through quite a lot. You can just convert this back in to pascals, and then you'll know exactly what that is. But the point of this exercise from this question, it looks like, let's see, how well do you understand these manometers and then pressure readings. So first of all, because of the fact that, so we have mercury inside of here, this tells us that we have 78 millimeters, okay, of height. That's the height, so that's the H. So this is going to be 78 millimeters. That's how far it actually rose. So that's where millimeters of mercury comes from. Okay, so this is the millimeter, which is the height. That's this height right there. And then mercury is because we have the mercury as the fluid in the manometer in the device. Now 78 is the same thing as saying 0.078. Okay, this would have been meters because there's 1,000 millimeters in a meter, or you can just use your prefixes and then shift the decimal over 3 spots. So we have that, so that's in metric standard units. Okay, density, okay, so that's in metric standard units, so that's what we have in there. And now we want to be able to figure out the rest. So the gauge pressure, so this is kind of how it works. Okay, so within here, so okay, I'm gonna just draw a line, okay, right there, because the pressures, okay, on both sides are going to be equivalent. So meaning this pressure right here and then this pressure right here, they're equivalent. So because you're in a fluid, so the pressures at the same depth, okay, so they're exactly at the same depth, are going to be identical. So what we have is P1 is equal to P2. Now, what happens is that P2, so as you can see there, so this is the PA, so it's almost like the absolute pressure. So that's this pressure right here. That's the only pressure you have because it's, this is the top of the fluid. But on the left-hand side, so what you see there is you have the atmospheric pressure coming from above plus the pressure which is going to come, okay, from the fluid itself at this particular height. Right? So this is going to be the pressure. Now the pressure, okay, so at a depth, so it's going to be the actual density times gravity multiplied by the depth, okay, or the height. And these two are going to be equivalent, right? So this is what you actually have in there. Now, as you can see here, so kind of from the definition of the gauge pressure, so gauge pressure, so that you have, really, okay, is that the absolute pressure is equal to the atmospheric pressure plus the gauge pressure. Well, okay, so notice atmospheric pressure plus gauge pressure. So this is actually the gauge pressure in here. And that is the reading that we have, which is given over here, which is given in the question here. So 78 millimeters of mercury. So we know that this is 78 millimeters of mercury. Now let's take a look based on the given information if they do actually equate. So the density, which is 13.6 times 10 to the 3, multiplied by gravity, which is 9.8, and then multiplied by the height, which is 0.078. Okay, so this is going to give us the answer in pascals. So let's take a look. So this is going to be 13.6 times 10 to the 3. Then this multiplied by 9.8 and then multiplied by 0.078. So this is, I'm going to just write it all out. So this is quite a bit of pressure in here, but this is in pascals. So now if you want it, and they give us the conversion, 1 millimeter of mercury is equal to 133.322. All right, so let's take that out. Okay, so if you do the unit conversion now, which means you're canceling out the pascals, so we need our answer, and we're going to divide 133.3, and that was, I think, 322. All right, so that's what we have. And notice, okay, so what happens is 77.975, etc., and this is now millimeters of mercury. Well, you know, as you can see here, so if you round this up, okay, even if you round it to 3 sig figs, okay, so this indeed will change to 78 millimeters of mercury, which is exactly what the reading was. So this is a pretty good exercise, and I guess it relates it back to kind of blood pressure readings. Not that you have to actually know about blood pressure, but you do have to know about fluids, and you have to know about the pressure in fluids. So the rise itself, okay, that's the extra pressure that we have. So what that means is our blood pressure, so in here, what this would mean is your pressure, your absolute pressure is, you know, whatever your atmospheric pressure is plus whatever the gauge pressure is. But the atmospheric pressure, of course, you know, as long as you're kind of on the around the Earth's surface, you know, that atmospheric pressure is always present. So really, this is the only change. So that means that the blood pressure is 78 millimeters of mercury higher than the atmospheric pressure. Okay, so that's another really nice example here. Next example. So we have a small cargo ship, okay, has a metric mass of, okay, so it's massive, okay, so these ships are enormous. You know, and most often, you know, they're kind of out of steel, you know, they're floating around, and we're thinking like, what the heck, how is this not sinking? You know, it's enormous. And that actually comes from Archimedes's principle and the buoyant forces. Okay, so if you have a buoyant force, those are the forces which are actually upward anytime you try to submerge anything inside of a fluid. So within here, we have this ship. And so the ship has a mass of 3,500 tons. Now notice a ton, okay, is, you know, 1 ton is, at least metric ton, is 1,000 kilograms. So this is going to be times 1,000. I'm going to just write that out in here. So this is huge, okay, amount of mass, okay, in here that's sitting on top of the water. Now the ship itself is made out of steel, and yet it does not sink. So if the ship has approximate dimensions of 50 meters in length, 30 meters in width, and 30 meters in height. Now, you know, ships are not necessarily rectangular, okay, prisms in shape, because they, you know, in terms of trying to move through the water, wouldn't be the greatest. So as you know, it's kind of pointy in certain directions. But for the terms of calculations, this is a little bit easier for us to do. So what we really have is, you know, so we have this ship. So I'm going to just kind of draw this out. And I'm going to try, you know, to duplicate it. Okay, so within here, so it's kind of like a rectangular shape that we have. And of course, I'm probably going to botch this because of the number. So 50 meters. So that's kind of the length of the ship. 30 meters. Okay, I didn't do a bad job, which is the width. And then we have a height, okay, right there. And that height is also 30 meters. All right. Now, the ship is mostly hollow, right? So like inside of here, so right here, it's pretty much hollow, okay, as you're going through. If it wasn't hollow, that's actually what the problem would be. And it would most likely sink, right? So it just depends. Okay, the water can only hold up so much. So in here, so what's happening is it is asking us, okay, so based on this, what portion of the ship is submerged in water? You know, so how many meters into the water does it go in? You know, so water is going to be, you know, floating, okay, around here, okay, as you're going through. And we want to know, okay, so like what is this depth, okay, that it actually falls under if it carries so much mass? Now we're going to assume that water is 1 gram per centimeters cubed, so that's very common. to assume, and this of course means that this is the same thing as 1,000 kilograms per meter cubed. All right, so this is what we have. So now everything is kind of in standard units. So now how are we going to use Archimedes' principle? Well, so it turns out that whatever you place on top of the water, you know, it will displace the amount of water, okay, as the actual weight that it carries. So this has a certain amount of weight, right? So this weight is pulling it down. Now that weight is just mass times gravity, okay, that we have. So we know exactly what this is because we know the mass of the ship. This is going to be 3,500,000 times 9.8. So that's the weight, okay, of the ship. And now the buoyant force, okay, is going to be upwards. It's going to be trying to hold this thing up. And it's going to be, the buoyant force is equivalent to this, right? As long as this thing is kind of floating on top of it. Now, if this is the case, if this is actually the amount of force that the fluid is, you know, upholding this particular ship with, okay, because it doesn't actually sink, so it doesn't go down, then now we kind of have to use Archimedes' principle. And what it states is, okay, if it can do this, then that means it's going to displace that amount of volume, okay, of water, which is going to have exactly that particular mass, okay, so within here. So we have this huge number, okay, or this huge force, and this is equal to, so the weight itself, so this would be the weight of the water. So this is the water that is, you know, displaced, okay, that we have. And now, so what we want to be able to do is, all right, well, we don't know the mass of the water, but we know the density of the water. And if you recall, so density is just mass times volume, which means mass is just density times volume. And so we can substitute that in here. So that's our mass, right, that we have. And this is going to be times 9.8. And so now, so from that, that's going to be the amount of water, okay, that we have. And this is equal to this. So let's substitute everything back in here. 3,500 and 000 times 9.8 is equal to, so this is density times volume times 9.8. Notice the 9.8, because it's on both sides, will cancel. And we're after actually the volume here. Now, why am I after the volume? Because I want to know, right? So what I want to know is, I want to know how high this goes. We already know that the ship is, you know, so we know the surface area. We just don't know how far this goes up. Okay, so all the way around. So we want to know this piece, right, of water that gets displaced by this cargo ship. So that's why we need to know what this volume is. Okay, so how much volume is it? And that's actually not very difficult, because it's going to be just the mass that we have in here divided by the density. All right, so this is, you know, much easier for us to do. Okay, so notice this is going to be 3,500, and that's the volume, so meters cubed. So that's what we have right there. And now I have to go back and I can, you know, say that, okay, well, what is the volume? So this has taken on a rectangular shape, right? So this is kind of a rectangular prism. So we know exactly, okay, so everything except, you know, how high it is. So this is 50 meters, this is 30 meters, and now we want to know how high that is. So that's the volume. So 50 times 30 times the height h is going to be equal to this. All right, so let's try it. So let's put this in the calculator. So I have 3,500 divided by, so 50 times 30, closed. All right, so it's just about 2 meters. So 2 to 3 significant figures, 2.33 meters. So that's the height, okay, of the boat that would be submerged, right? And that's it. So I mean, it's, you know, it's pretty high up. I mean, 2.3 meters, you know, in terms of submerging, well, if the ship is 30 meters, okay, up on top, So it hasn't submerged too much, okay? And if you can imagine, if you keep loading this cargo ship and putting more and more weight on it, the ship will just sink more and more and more because of the weight that it would carry, right? So we obviously don't want to put too much stuff onto the boat, because then eventually, it's going to get very, very close all the way to the top, okay? And then, we don't want to sink this particular cargo ship. So there you have it. So that's this example for you. Here's the last example. So we have a bent pin, as you can see there in the figure. It's suspended on top of mercury. We want to find the total surface tension in the vertical direction that supports the pin. So, of course, in the horizontal directions, the tensions cancel themselves off, so they're not really supporting anything that is suspended on top of a fluid. So we'll just look for the vertical pin itself. Now, we'll assume that the linear coefficient of surface tension for mercury is 487 millinewtons per meter, and the actual angle, okay, so once the pin is suspended, okay, it makes a 45 angle with the vertical, so just as it's kind of shown right here. So let me maybe also illustrate it in this way. So if you have the pin, okay, like this, you'll have kind of the surface tensions. Okay, so there's going to be kind of like a bend right there, and so it makes a certain angle, and this angle in our case is 45 degrees, right? So we need that angle, because if we want to know what the vertical component of the tension is, we're going to need to try to figure that out. Okay, so first off, the surface tension itself, so for example, okay, what we have, so the coefficient is just nothing else but the total surface tension divided by the total length that you have something which is being suspended on top. Now, this particular length that we have, so that length, if I kind of blow this up here, we have to go all the way around here. So this length, okay, so the tension is present all the way around. So as you're going all the way through, so we're going to have to know, what that length is. All right, so that's maybe the first thing that we'll do. It's going to be the most annoying component for us. So the length itself is equal to, so let's start off here. So 5 centimeters, we're just going to go one by one, plus another 5 centimeters. So that's that. Now it depends. Most of the time we may not actually count the little tips, okay, so these, but because I guess they give us the dimensions here, okay, so notice that the width, okay, so this particular little width is 0.02, so I will count it, plus 0.02 centimeters, so that's that. Now we got to go back, so it's going to be from here and up to here, so that's another 5 centimeters that we're going through, plus, now be careful, it's 5 centimeters up to here, right? So then you have this little extra piece right here, and that extra piece is going to be the same thing that we're dealing with there, which is 0.02, plus again a little extra piece in here, so from here to here, so that's going to be 0.02 again, okay, and then now we're back, okay, so now it's from here to here, which is going to be 5 centimeters, so that's almost everything. And then finally we need this little piece right there, so that's going to be from here to here, and so that will be 2 pi r. Now the radius is 0.01 because it's half the diameter, and we have to divide this by 2 because it's only half the circumference, right, that we're going through. So this is, I mean, it's kind of annoying, but let's see what this gives us. We get 20 centimeters, 0.91, 4, etc. So these little pieces, okay, so this this whole thing really is just coming from those ends that we would have. So that's why, as you can see, most of the time people won't even consider those particular ends, but I mean, I'll do it anyways. So now we're after the surface tension right here, so our formula is going to be the total surface tension is equal to, okay, so it's going to be that. So that's the surface tension that we have. Now, if you want the vertical component of this, because the way that it's drawn out here, so as you can see there, So your surface tension is in this direction. But if you want the vertical component, okay, of that piece, okay, the horizontal components, because the surface tension is on both sides, okay, as you're going all the way around, so the horizontal ones will cancel. But the vertical component you can obtain right there. And so that would have been, well, so in this case, it's this vertical component. Now we know this angle, which is 45. Now, if this is 45, so is this. So how you do it is up to you. Now, if this is 45, this is just going to be kind of cos of the angle itself. So let's substitute everything back in. So I have my coefficient. So now it's in millinewtons. If you want to change it back, 0.487, that's going to be in newtons per meter, multiplied by, now I can get this in meters as well, so 0.20091, etc. And then times cos of the angle. Now the angle is 45 degrees, so this is just 1 over square root of 2. You can plug that into your calculator, okay, and then see what happens. All right, so I'm just going to take all of these numbers and then multiply them, and just to see what that surface tension, that vertical surface tension would be. All right, so there it is. Okay, so it's very tiny, and of course we don't suspect that it's going to be very big because it is still a particular fluid, right? So that you have in there. So if it's just suspended on top, you can change this if you want to millinewtons, so it'd be 69.2 millinewtons, but we'll keep it in SI units. So that is pretty much it. That's all that you would have to do with this one. Okay, if you want to see more surface tension kind of examples, I can put up a link up above there and kind of goes into the explanation a little bit deeper. All right, so thanks for watching. Okay, we'll see you in a future video. Bye, everybody.